Question number 3 from my 1994 Microsoft internship interview was actually the most interesting question of the 4. It wasn't necessarily the hardest. It was actually probably easier than question number 4, but it's much more interesting, and actually in a modern context is really kind of, it almost seems like prescient at the time, or it seems like something where people were doing something interesting way ahead of where the hardware had actually gotten to at that point, at least in the desktop space. Now, this question was way too hard for me. I wasn't really that good with binary. I knew what the different things were, but I wasn't good enough at solving binary puzzles, basically, to do this one on my own or to think through how it would happen. I did eventually get it on the whiteboard when the interviewer gave it to me, but only because they really helped me out. They kind of prompted me and gave suggestions, right? And without that, I never could have gotten it at all. So the background for the question, which is flood fill color detection, is that in those days, graphics libraries oftentimes, at least for things like, BASIC or whatever, or even probably higher end ones, I don't know, I didn't have any access to higher end graphics libraries at the time. But even in things like BASIC that came on home computers, or that were sold in stores, have the ability to do this thing called a flood fill. And a flood fill is just when, you are writing some basic program and, you draw some lines or something on the screen. You end up, I kind of drew like a crooked heart for some reason. You can then pick a pixel and you can ask it to flood fill that pixel with a color. And what it'll do is look at what the color is of that pixel, and it will expand outwards from there, filling all of the pixels that it touches. And this will make it fill in the entire shape. Now, at the time, computers were very slow, and so this was an operation so slow you could watch it happen on 8086s. You could literally watch it kind of go It's kind of fun to watch, but, if you were actually trying to get something painted on the screen quickly, not very much fun. Now, we don't tend to do this anymore because it doesn't really work with graphics pipelines very well, so you typically won't see this in something that's actually trying to draw images to the screen. You might see it as the paint bucket tool in something like Adobe Photoshop, but you don't see this in graphics libraries. Typically, the way we do this in graphics libraries nowadays is this thing gets tessellated, into a bunch of triangles somehow, and then you send the triangles down a GPU pipeline, and that's how you would fill shapes. So we don't really fill shapes the same way. But in those days, this was very common. Now, in order to do this, this was for 4-color CGA mode. This was a particular mode where you could have 4 colors on the screen, and I don't know if it was 320 by 240 or 320 by 200 maybe might have been the resolution, but these are very low resolution by today's standards, and only 4 total colors. And the 4 total colors were just the primary colors or the secondary colors. It was cyan, magenta, yellow, or red, green, blue, or something like that. And I think it was actually kind of a brown. I don't even remember. You can go look up CGA displays and see these modes for yourself. They're very primitive by today's standards, but that's what we had at the time. And BASIC had a fill for one of these modes, and the person at Microsoft who was interviewing me had worked on their fast flood fill algorithm for some kind of Microsoft thing that I think was in BASIC, that it was some kind of Microsoft BASIC product or something like that. I don't really remember because I don't know the details of that product. He just kind of mentioned it as part of the interview. So in that mode, pixels are 2 bits because there's 4 colors per pixel. That means that a byte, which of course has 4 separate 2-bit values, right? For 8 bits, we have 2, 2, 2, 2. So that means that you're actually going to get 4 pixels in here. There's pixel 0, pixel 1, pixel 2, and pixel 3, all packed into 1 byte. That's how it was stored in memory, and that's how you had to draw to the screen. So if you wanted to fill a particular pixel with a particular color, for example, you had to actually modify just one portion of a byte. You couldn't write the whole byte with a new color. You had to preserve the pixels that you didn't want to touch and just, you'd have to AND them out and or in a new value and write that byte out to update, say, just pixel 2 if you wanted to. So this brought up an interesting challenge for them when they were working on this fast flood fill, which is when you are doing the flood fill, as I described it just before, it's you pick a pixel and anything of the same color is supposed to get flood filled out. So there's kind of this algorithm of doing this fill where you kind of walk through space finding colors that are the same pixel as the one you started with. That relies on some basic color detection. You have to be able to find which pixels that are nearby to you are actually the same color as the one you started with. Now, normally, if bytes, represented a pixel themselves, you'd just be doing, an equals operation on the pixels that were nearby. But because pixels are actually packed 4 into a byte, it means that now you need to do this kind of color detection inside the byte itself to figure out where the colors are. And what they found in making this, fast flood fill was that a key to making the algorithm run quickly was having some way to take a particular byte with these packed pixels in it and figure out if any of the pixels in it matched the color, so that they didn't have to actually go through and figure out which ones did using some kind of slower process. The interview question was, what can you do for that, right? Basically, like if you had to implement this fast check that said, here is a particular 2-bit color, right? So a number between 0 and 3, basically, that's your starting point. Tell us whether or not a particular byte that we hand you happens to contain that color. So if you think about what has to happen here, we have a color value. That color value is going to be some number, right, between 0 and 4. So let's say it's something like 3. And we know that in a 2-bit representation, 3 is 1, 1, something like this. Then when we look at a particular byte that has this 4-pixel packing to it, if we imagined, let's say there's a byte that has all 4 colors in it, right? And by the way, the reason there are 4 colors is because black was one of the, not having one of the things lit was one of the colors. So if we had 0, 0, 0, 1, 1, 0, and 1, 1, if we had all of these in a single byte, we would want this to return true because there is some way, like our function that does the test should say yes, because there is a pixel inside this byte that does contain the color we're looking for. On the other hand, if we had one that did not, right, so it was something like 0, 0, 1, 0, 1, 0, 0, 1, no 1, 1 value, we want this to return false. So this had to return true, some non-zero value, and this had to return false. So this has to return 0. That's effectively what they were asking me to do on the whiteboard. Now, this has a very easy solution if you know binary but aren't really very good at it. All we would really have to do is write a for I loop from 0 to, less than 4. So 0, 1, 2, and 3, loop over those values, and shift this value that we're given down by 2 times the number that we're iterating. We would just shift down into each position. Then we would mask out the top part, right? We just do an AND with, 3 to just get the bottom 2 bits, and then we would check to see if they were equal to the color we were given. Now, this would be fantastically slow especially on old processors where loops were very expensive and things like that. You'd probably want to then unroll that loop, and it would just be a bunch of code. So it would be kind of slow to do that, right? You definitely wouldn't want to write in a loop. You just want to write it out 4 times, copied. But all those shifts are expensive. There's a lot of different ands and all that sort of stuff. So the baseline version of this is not nearly as fast as you want it to be. And the question is, what can you do that actually does that faster? Now, if we consider what is going on at the bit level here, one of the really interesting things, and I don't think I'd ever really thought about this at the time, this is the first time I really, anyone had asked me a question that really provoked my thinking about it. If we think about the operations we actually have when we're working at the bit level, there is one particular operation, which is XOR, which effectively does a bit level comparison. Now, this is not the way I think I had ever thought about it before. But if you look at how XOR is structured, just the way that it actually works with values, if you look at like the truth table of it, right? If you looked at like, oh, I have a 0 and 1 in one of the values, right? And I have a 0 and 1 in the other value. If you look at the XOR, it does exactly what its name implies, exclusively OR. So it's basically if the two values are equal, it will not be true. If the two values are not equal, it will be true. It's exclusively one or the other, right? So in this case, if it was 0 and 0, we would get 0 because those are the same value. If it's 1 and 1, we would get 0 because those are the same value. If it's 0 and 1, however, in either pair, we would get 1. So if you look at this versus an equals operator, which we don't really have in binary exactly, there isn't like a thing that's like EQ exactly. We don't call it that. But if you imagined the truth table for this like are the bits equal operator, what we would end up with is exactly the opposite of this pattern. In other words, if we look here, we would say equals 0 and 0, well, that's true, they are equal. 1 and 1, well, that's true, they are equal. 0 and 1, not equal. 0 and 1, not equal. When you look at these two truth tables, you realize that XOR is basically not equal to, right? And again, it's perfectly obvious to any experienced programmer that that is true. But to a novice, which I was at the time, I'd never thought about it that way. I kind of knew what an XOR did, but I just didn't ever think of it as being the opposite of equals. So what this means for our problem is if we imagine, again, and we can use our this was a nice test case, right, that I wrote out before where we basically have all the different colors packed into one. If we look at what happens here, if this is our input, we can pre-construct, because remember, the color we're looking for stays the same throughout the whole flood fill. We can pre-construct whatever that color is. Let's say it's 1, 1 again. We can construct a byte which just has that value we want in every single slot, in each pixel. So this is our, test, right? This is our test byte that we're using. If we were to do an XOR on these, we will get effectively not equal to, right? So when we look at 0, 0, and 1, 1 here, well, these now become individual because the XOR does not look across bits. But so when we actually look at what we end up with in the result, if we actually do our XOR, we get the exact opposite of the equals. So these ones both become zeros, right? Because they are not different. This becomes a 0, but this becomes a 1 because there is a difference there, right? This becomes a 1, this becomes a 0, so these flip. And in this case, they are both 1s because neither are the same. So again, this is effectively a not equals operator. What that means is if what we're trying to do is look for equality, we want to see if something matches, all we have to do is do the binary not, flip the bits. Now, we effectively have a byte which has 1s, right, because we're going to not these, that has 1s everywhere that are bits matched up. And all we really need to do now is figure out some way of figuring out if we had 2 1s in a particular slot as opposed to just 1 1, right? Because if we had the opposite thing, if we didn't have any that were mixed, we would just be done, right? Because we just go like, okay, is the value non-zero? We're done. But the problem is some of these have like 1 bit that matches and 1 bit that doesn't. If both bits match or neither bits match, we're actually done after the not. But we've got this problem of some that are a mixture. But of course, we have a way of lining bits up. That's a shift, right? We can shift bits left or right, and we can actually produce bits that line up. Now, we do have to be careful here, right? Because if we want to shift bits over, well, all the bits are going to shift over. That means that if we were trying to line up bits so that we could, say, line up this bit with this bit to do some kind of test on them, we would also be at risk of this bit shifting over into this position, for example, right? So what we need to do here is first, we need to mask this off. We need to make sure that we're only going to shift over one of the bits and not allow the other bit to contaminate across the boundary. But again, very easy to do in binary. We can AND this value with a mask that picks out the bits that we want, those first bits. If we have a mask of 10, 10, 10, 10, we can pick out just those bits. So for example, we can do an AND of this with this, and we will just get those leading bits. Now we have 10, 10, 00, 00. Yeah? We shift this over, and this, in particular case, we are going to be shifting to the right, right? So if we want to move this over to the right, we can now go, all right, we shift these over to the right. This is going to be 0, 1, 0, 1, 0, 0, 0, 0. Now we have a perfectly lined up version with our knotted version, right? And we can do the AND of these two to produce the final result that we wanted. Now, keep in mind that we've guaranteed now that there will be zeros in the first position because this AND knocked out all the other values, right? So there's no way we can have leading ones here anymore. They've effectively been removed by the previous operation. This, as a side note, if you remember from the first part, part one of this course where we learned assembly language, you will remember that there are two different kinds of shift. And you do have to be careful in this case to do a shift right that isn't going to shift in a 1 if the leading bit is 1. So you want an unsigned shift here, or a logical shift, right? So this is a logical shift here, not an arithmetic shift, which would have duplicated that 1 bit. But those are, again, they're equivalent on most processors. It's not like you pay more for one or the other. So totally the same cost either way. So it's free for us to guarantee there's a 0 in that position as well. If we now do one more AND by ANDing these two together, we will now figure out whether or not any of our patterns matched exactly, leaving us with a final answer, right? If we do all these ANDs, you can see that now our bits don't line up here. I'm sorry, I'm using the wrong one. Our bits don't line up here. So we're just going to get zeros in the places where we didn't have both bits matching. But in the one case where they both matched, you can see there's a 1 here and a 1 here. We will get our 1. So the entire byte, all 4 pixels, can actually be tested with 1 XOR, 1 NOT, 1 AND, 1 shift, and then a final AND. This tests for not equals. This turns it into an equals. This removes the values we don't want for our shift. The shift puts things lined up so we can test both bits, and the AND figures out whether both of the bits happen to match. Now, I'm 99% sure that is the solution that the person wanted, and that I ended up doing on the whiteboard only with a ton of help from them. I'm quite certain they left that interview thinking this person doesn't know binary very well, and that was true. However, my memory could be hazy. I don't know if this was exactly the pattern. It was something like this, but I don't know. I really loved this. This was like my favorite interview question of all of them. As I've said before in multiple places, I don't think this is a great style of interview. I think there's a number of reasons why I don't do interviews this way, and I don't think it's a good interview process. But if you put that aside and just think of it as something that was fun for me to do, separate from whether it made a good interview, I loved this. It was so educational for me to see. And if you think about what this actually is, bringing it forward to a modern context, this is basically doing SIMD, right? Single instruction, multiple data, the way we do it now in SSE or AVX or those sorts of things. We're effectively doing that. Packed single instruction, multiple data is basically an instruction set designed around doing exactly this. And the only real difference between the SIMD stuff and this stuff is that the SIMD instructions are built to avoid the extra work that we had to do here. So for example, In a real SIMD instruction set, which they did not have the benefit of using, you don't need to do this kind of thing. You don't need to AND out bits so that when you shift, they don't cross lanes, because SIMD shift instructions automatically don't cross lanes. So they effectively have that ANDing, that getting rid of those cross bits baked in. Now, that's not that big of a deal. It's obviously a speed improvement, but it's not that big of a deal for something like this because it's doing all these logical ops, which are pretty easy to mask off. It doesn't cost you very much. But you can see why it's a big deal for more complicated things like multiplies, for example, or adds, where you're going to do these operations and bits are going to cross potentially into the other lanes. And the only way to prevent those bits from crossing is to add lots of padding in between before you do the operation, which wastes all these bits. So this is super cool. It's basically doing SIMD without SIMD. Nowadays, you wouldn't have to really think about this stuff very much because we have SIMD instructions and we very rarely use values that are 2 bits long, right? 8 bits is usually the minimum. So having 8-bit lanes in SIMD, which we have, is all we really need. And we can get rid of things like this. Furthermore, we wouldn't have to do most of this stuff anyway in a modern SIMD thing because they have equality operators. So even the comparison operators we can now just use because they work in lanes. So much more complicated than a modern SIMD instruction set, but still fairly simple and just really cool that people figured out, oh, wait, we can basically do a bulk set of comparisons on 2-bit values by just, if they're all packed in a byte, we don't really ever have to expand them. We can just do all the comparisons right in place by being somewhat clever with our binary. So that's it for question 3. This is actually the kind of thing that we think about a lot nowadays, because even though back then they had to do this stuff without a SIMD instruction set, we now have a SIMD instruction set, and we have to think about this kind of thing all the time because the SIMD instruction set is actually the thing that is the very fastest for basically everything that you want to do on bulk data nowadays, whether it's copying the data or modifying the data, doing computations on it, searching it. SIMD is pretty much the only way to get modern CPUs to run quickly. So if you like that sort of thing and you would like to learn more about how SIMD works on modern computers, that's exactly what we're about to be doing in my performance-aware programming series, which is on computerenhanced.com. So if you like this kind of thing, please come check it out. We're about to be doing exactly this sort of stuff. There are so many interesting things about SIMD nowadays because the instruction set is all designed to support that kind of thing. And so this particular interviewer was way ahead of their time by trying to do things with multiple pieces of data inside a single byte. Nowadays, this is just how we do things. We don't really go sub-byte, but we do things in lanes exactly like that because that's how the instruction sets are set up. So check it out if you're interested. I'll be back here tomorrow to look at question 4, which is how to outline a circle. This one was a much more difficult question because if you don't already know the algorithm for outlining a circle, it is basically impossible to come up with. The person who came up with this style of algorithm in the first place was pretty brilliant, and it was a pretty remarkable thing when they came up with it, so trying to do it on a whiteboard is basically impossible. However, I already know the secret now, so I will be able to do it for you, hopefully on the whiteboard, even though it is somewhat complicated, because I know the trick. So that'll be interesting. And it'll still be a fun problem to go over, and it's a good trick to know because it does come up in lots of places. There are a lot of ways you can use this trick, and so it's a good one to know. I'll be back here to do that tomorrow. Until then, have fun programming, everyone, and I will see you on the internet.